All right, let's go ahead and get started. I do not have this room reserved for Friday, but it's my intention to be here Friday and just have problem solving for students. It's optional, right? So there you go. Any questions about that? Any questions as we get started? We're in chapter 7. Let's take a look at chapter 7. Today we'll talk more about the exergy, how to calculate the property exergy, and we'll establish the exergy balance for a closed system. Here are the main equations. I showed them last time. So for energy, for a closed system, you just have the internal, kinetic, and potential energy. For enthalpy, where it's an open system where you have flow across a boundary, you have the property enthalpy is of use. We use enthalpy, m dot times h. For exergy, this is the equation for the exergy. It's in terms of a lot of properties plus the kinetic and potential, just like the total energy was. And when we get to open system analysis, we'll have a flow exergy, just like enthalpy, and like that. There's the parallelism. Here's the derivation for the exergy. I could have wrote it all out as I went along, but it's in the book, and I try to follow the book so you can backfill as you read the book. But let me give you the derivation for the exergy expression. So if we want to derive the expression for exergy for a closed system, here it is. That's what we want to derive. We start with a system and an environment around that system. So the blue is the system. It's at a temperature and pressure. And the environment's at T0 and P0, the dead state temperature and pressure. What we're interested in, the combined system. Remember, exergy is a function of both the system and its environment properties. We want to develop an expression for the work out of the combined system, and that's WC. So that's what the subscript C is for. Now, this system can expand, and when it expands, it pushes back the environment. But the environment's not expanding and pushing back any. We're only interested in basically WC is a useful work transfer out of that combined system. So we do an energy balance for the combined system. And so you have the change in the total energy of the combined systems equal to the heat transfer out of the combined or into the combined system, but there's none. And that work that we're interested in computing. We take a look and we say, well, what is the change in the combined system energy? It'll be the sum of due to the system, and instead of writing SYS all the time, I thought I would just leave that subscript off. But that's the change in the energy of the system plus the change in the energy of the environment. What are we going to do? We're going to start that system at temperature T and P, and we're going to let that system go into thermal and mechanical equilibrium with the local environment and extract the largest WC out possible. So here's an expression for the change in that energy of the combined system when you expand the energy of the system plus the energy of the environment. But it doesn't make sense to have the kinetic energy of the environment. It's lethargic. It's just a big system that has a temperature T0 and pressure P0. So we strike those two terms. But the energy, the internal energy of the environment can change during that process from the initial state to the equilibrium state. So if I scoot down just a little bit, we'll see that the change in the energy of the combined system is you start at state U and you end at state U0. So the system goes from the initial internal energy to the dead state internal energy. Then you have minus the change in kinetic. Well, actually, this change in kinetic is the final kinetic energy of the system. Well, that's when it's in the dead state. So that's KE0 minus KE. Well, KE0 0. So you're just left with minus KE. You follow that logic? Likewise, for the PE, the potential energy, The change in the potential energy is just negative the initial potential energy of the system. Okay, so that we simplified this term in that energy balance. If you take a look at applying the first law of thermo only to the environment, that's just the environment only. You have the change in internal energy of the environment, so we can work on this term right here, is equal to the integral of the sum of the heat transfers. And now that is the heat transfer into the environment using our thermodynamic sign convention into the system as a positive Q, minus any work out of the environment or by the environment. Well, what is the work done by the environment? It's, as we've shown here, well, let's take the heat transfer first. Note, you can have a heat transfer into the environment. If it's into the environment, it's out of the system, the blue system. But there's no heat transfer from the environment to anything else other than just the system. Now the work. So the integral of the work of the environment is equal to, if the system pushes into it, it'll be the integral from the initial state of the environment to the final state of the environment of the constant pressure of the environment dV, integral PdV for the environment. Well, that's equal to just P naught V naught minus V. But that's the environment volume. We notice that if the system expands, the environment is compressed a little bit, or not really compressed, but the volume change. So the volume change of the environment can be related to the volume change of the system by the negative sign. So all I did was put a negative sign there, and now instead of talking about the final dead state volume of the environment and the initial volume of the environment, it's the dead state volume of the system and the initial volume. Does that make sense? That's a little tricky right there. Okay, now we can substitute those two expressions for the Q and for this P delta V term into that first law for the change in internal energy of the environment. We apply the second law only to the environment to get an expression for the change in entropy of the environment. We see that it can be increased by bringing in heat with it. With the heat transfer into the environment from the system brings in entropy. The boundary temperature is the environment temperature T naught. And you can have some sum of entropy generation in the environment. Okay, well, that's kind of a fancy expression. Just turn that into sigma environment. That's the amount of entropy generation in the environment. Okay, so if you take this equation, multiply by T naught, and rearrange, you get this equation. See that? So now we have an expression for the integral of del Q. All right. So take this expression for delta U plus this expression for the second law of the environment, combine them, and you get an expression for the change in internal energy of the environment. Here it is. That's algebra. A few steps there though. And then we'll do this. We'll combine that result with this result and rearrange terms. And we find that the change in the energy of the combined system can be related to, and it's starting to look like what we need it to look like. We have the second law for the entire system. The entire system has no heat transfer with the surroundings of the entire system. But you have entropy generation both attributed to inside the environment as well as in the system. So we rearrange this. We multiply that equation by T naught. And what you do is you now have an expression for this term and this term. And so you can replace those with this. It's algebra. And what you get is an expression for the change in the energy of the combined system is equal to all these properties with, now we have it T naught times the change in entropy of our system and the entropy generation due to irreversibilities in our system. Okay, at this point we're interested in what was WC again. It was that work out of the combined system. And what we find is that that work out of the combined system this was our first equation. Let me see, I should have written an arrow like that. Right here. So the negative work out of the combined system is the change in the energy of the combined system. We now have an expression for the change in energy of the combined system. So we can put it into here. And now we have the work out of the combined system is equal to a change in U times P naught times a change in V, T naught change in S, kinetic potential energy, minus T naught times the entropy generation due to irreversibilities. So what we find is this is a group of properties. All of here is just, all these are properties plus the kinetic and potential energy. So if you want the maximum work out of the system, this needs to be set to 0, doesn't it? No irreversibilities lets us get the maximum work out of that combined system. And then we see it's just now you call this the exergy because it is a new property. It's a long group of terms, but there are the terms. The derivation is also in the textbook, but there's a Cliff Notes or even maybe even not to. That derivation isn't short, is it? It takes us a while to do it. Okay, and there's a lot of places to make a sign error. But let's move on. Let's apply this to a problem. So we want to calculate the exergy of a concrete block given a temperature and pressure for that concrete block. So the mass of the block is 3 kilograms. It is concrete. The initial temperature is 80 degrees C, and the initial pressure is 4 bar. The system is at rest, so the concrete block isn't moving, and it's at 0 elevation in the reference environment. The dead state temperature is 20 degrees C, which is 293 Kelvin, and the dead state pressure is 1 bar, which is 100 kilopascal. We want to calculate that exergy, the current property known as exergy, in units of kilojoules for this concrete block. So exergy is going to be the mass times U minus U naught plus P naught times V minus V naught minus T naught S minus S naught plus any initial kinetic energy, lowercase ke because I have the mass outside, and lowercase pe for potential energy. From the problem statement, the potential energy is 0. And the kinetic energy is also 0. True? Okay. So now the goal is to say, which properties do I know? Well, I know that it's 3 kilograms. And I need to calculate kind of like group 1, group 2, and group 3. You know, what is this delta U, U minus U naught, for this problem? So this is the internal energy of the concrete, the specific internal energy, at that temperature of 80 degrees C and pressure 4 bar, right? So how do I calculate that? All right, let me pause for a minute and let you think about this and write down some things, and I'll go around and check you. So what you do is you find that concrete is a solid. And in Thermo 1, what did we learn about things like liquids and solids? Okay, I'm looking for another one. How about incompressible? They're incompressible, meaning that you can increase the pressure, but what doesn't change? The volume. The specific volume is constant. So right away, which group of these terms is easy to determine and is equal to 0? The middle term, 2, because V minus V naught. So the concrete starts at 80 degrees C and 4 bar. It has some specific volume. We don't know it. It's a reciprocal of the mass density, so you could look it up in the table. But when it goes to 20 degrees C and 100 kilopascal, it doesn't change volume. So what is this term that's equal to 0? So the whole middle term is 0. Got it? True? It's incompressible. All right, now how do I calculate the change in internal energy for incompressible substance? Hey, let's use that specific heat, true? So that's going to be C T minus T naught. Is that true? Yeah. And then over here we have minus T naught. Now I need to calculate the change in entropy. How do I calculate the change in entropy of incompressible substance? You have to reach back way into your recesses from Thermo 1 and recall specific heat natural log of the final temperature. It goes from to initial temperature, but here we're going from S naught to S, so it's T over T naught. It's like this is from initial S1 to final S2. I know that S naught is our dead state, it's our final, but when you have a delta S, there you go. Hopefully that's understandable. So what you can do is you pull out that specific heat and you're left with T minus T naught times natural log of T over T naught. True? And so for concrete, we had 3 kilograms. What was the specific heat you found for concrete in that table? 0.880. What are the units on that? Kilojoules per kilogram Kelvin. All right. Now we have T minus T naught. So it's 80 minus 20 degrees C minus T naught, 293 Kelvin, natural log of T, which is 80 plus 273, divided by T naught, 20 plus 273, or just 293. Okay. I'll always get a question like this: Professor, I'd like to cancel these units, but how can I cancel a degree C with a degree Kelvin? The difference, temperature difference, is precisely the same. The size of 1 degree C temperature change is exactly 1 degree K temperature change. That's why you can cancel them. It's a temperature change. Okay? All right. This other converting, canceling Kelvin and Kelvin, that's great. But why do we have to put in here? Why can't we put in 20 degrees C right here? Because, hey, you said degrees C cancels with degrees K. But this is a temperature difference. Can you see it? 80 minus 20. This was just the temperature. And when it's just the temperature, you have to have the absolute scale. That is very subtle. No matter how many classes I teach or even what level I teach, I have to re-explain that concept. So please struggle with it. You'll be far ahead of your colleagues if you get this concept down, especially when you go to heat transfer, which is another class that you'll have to take. Yes, sir?
So I guess it'd just be easier just to initially just put all the temperatures the same.
You're absolutely right. And then what you'll find is you'll go on a longer path and you'll get to the exact same result. So what you do here is you say, look, I'm going to put 80 plus 273. And then I'm going to have minus 20 plus 273. I convert the 80 to Kelvin, the 20 to Kelvin. But you can see that that conversion goes away.
I mean, if you have issues where
go slow. Make sure you grasp the difference. But after a while, you'll be able to say, oh, in this case, it's a temperature difference. 1 degree C change is exactly 1 degree K change. Yeah. Okay, and then you can compute the final answer, chase your units, and I think you get 14.3 kilojoules. Any comments or questions on this one? Did that help? Let's go to another problem. So, exergy of liquid mercury. Mercury at, so we have a system consisting of 2 kilograms of liquid mercury at 50 degrees C and 3 bar. So you might want to put over here, okay, the temperature initially is 50, pressure 3 bar, and the system is at rest and 0 elevation, and the dead state temperature is 20 degrees C, 293 Kelvin. Dead state pressure 1 bar, which is how many kilopascal? 100 kilopascal for 1 bar? Right. And we want to calculate the exergy of the system. It's the same equation we had. E is equal to M times U minus U naught plus P naught V minus V naught minus T naught S minus S naught. And I neglect the kinetic potential energy because they tell me that. So what do we know about liquid mercury? It's incompressible as well. So even though it's changing from 50 degrees C down to 20 degrees C, this term is 0 in that calculation. And we do have the same type of equation, M, C, T minus T naught minus T naught, natural log, T over T naught. And there you go. So that's how you would calculate the exergy. You have to go to the same table to get one value for liquid mercury, and that's the specific heat. And the specific heat of liquid mercury is 0.139 kilojoules per kilogram Kelvin. And sticking in the numbers, I'll give you the answer so you can calculate the thing. 0.40 kilojoules. So liquids as well as solids, some liquids and solids are incompressible. A good approximation. Ready to go on? Okay, exergy change. We're going to deal with now a change in exergy where the system doesn't go from initial state all the way to the dead state. It goes between two states. So we're interested in what is the exergy change, and we usually put it like this is the initial state and this is the final state of a process. True? So you could do it this way. You say, well, what is the initial or the final exergy? That would be U2 minus U naught plus P naught V2 minus V naught minus T naught S2 minus S naught. Then subtract the initial exergy U1 minus U naught plus P naught V1 minus V naught minus T naught S1 minus S naught. Well, we see a lot of cancellation, don't we? Those terms cancel. These terms cancel. These terms cancel. And we're left with a much simpler result that it's just U2 minus U1 plus P naught times V2 minus V1 minus T naught S2 minus S1. So when you calculate the change in the exergy, the dead state temperature and pressure still come in, but you don't have to have U naught, V naught, and S naught. Make sense?
So is this like a change from one state to the other?
That's exactly right. And often those are what we have. We have processes that don't always go to the dead state. They just go from this state to that state. And that's a good lead in to a derivation. So let's go ahead and do this derivation. So it says derive an expression or the expression for the closed system exergy balance. Well, here is the equation right here out of the textbook. So what we have is we say for an exergy balance for a closed system, you have the change in the exergy from initial to final state is equal to a term that looks like exergy is being transferred with heat, as well as the work minus this boundary work of pushing into the environment. So the system, you want to get the useful work out of the system, but if it pushes back the environment, that's a non-useful component. So the sum of W minus this term is what we call the useful work, shown here. In the previous discussion, it was WC. All right. And then we have this term right here. Well, what is sigma? Entropy generation. And so if you multiply entropy generation times T naught, it's a term that is going to be called the exergy destruction. Entropy generation, exergy destruction. So this is our exergy balance equation. Is exergy conserved? No. Exergy can be destroyed if you have sigma, if you have irreversibilities. If there is some entropy generation, there will be exergy destruction. So it's a minus for the destruction, T naught times sigma. We want to derive that. That's the goal. So what we do is we start out with our system, thinking that it's going to expand into the environment, as well as produce useful work out of the combined system plus the environment. We have the first law process, apply it for the system only. So you have the change in internal, change in kinetic, change in potential energy of our system only, equal to the sum of all the little heat transfers, or Q's, heat transfers, into our system, minus this work. Now that work is the combination of the useful work and pushing back the boundary, expansion, against P naught. All right? So that we can substitute for that work. We also write the second law for the system. So the change in entropy of the system is equal to integral del Q over T plus sigma. If there are irreversibilities during the process, this term will be non-zero. We multiply the second law by T naught and subtract it from the first equation, or the first law, and you get this relationship right here. A lot of those terms are just the first law, but the other terms are T naught times delta S from here, right? You multiply this equation by T naught and then subtract it. So you pick up that term right here. You also pick up minus T naught over T in the integral del Q. You have that useful work minus this PV term. I expanded that work term. And then you have minus T naught sigma. So there's some algebra. Take this P naught V2 minus V1, move it over to the other side. All right. And now you have an expression that looks like this. Oh, this term also move over in relationship, put it right there. So what we have is we have change in U plus P naught change in V minus T naught change in S plus kinetic plus potential energy. That is simply the change in the exergy, is it not? That's our exergy change. And that's equal to this integral 1 minus T naught over T del Q minus W useful minus this term, which we name now exergy destruction. So you can write it very shorthand. Exergy balance is the change in the exergy of the system is related to exergy transfer with the Q, with the heat transfer. How do I calculate it? It's this right here, integral 1 minus T naught over T del Q. So there is exergy transfer with heat. Analogously, was there entropy transfer with the heat transfer? There was. And this is kind of a silly question. Was there energy transfer with the heat transfer? Yes, yeah, yeah. Okay, then you have right here this E sub W. Well, what was that? That's this term. It's our useful work transfer. And that is simply 1-to-1 a work transfer out of the combined system. That's what can be used to, as the book describes, raise a weight in a gravitational field or turn the shaft of an electric generator or do something very mechanical work. And then E sub D is the exergy destruction, and it's equal to T naught times sigma, the entropy generation. So there's our exergy balance equation. All right. Any questions on the derivation of the exergy balance equation? It's also in the textbook. That's one reason why I wrote it here, so I can go a little faster. Hopefully you'll see the big picture and won't get too bogged down. Ready to solve a problem. Let's go back to this problem. So we're asked to calculate the change in exergy of propane as it's heated in a piston cylinder apparatus. So the propane is initially at 3 bar and 30 degrees C, and it fills a piston cylinder apparatus. What does that look like? It looks like, here's our cylinder, there's our piston, it has some weight on it. The weight basically dictates the pressure of the gas trapped inside the piston cylinder apparatus. So this is our closed system. That's the propane. Okay, the propane is heated until the temperature becomes 90 degrees C. So we start at state 1. The temperature 1 is 30 degrees C. Pressure 1, 3 bar. You go to state 2, the final state, temperature 2 is 90 degrees C. Now, what I encourage you to do is write down all of your thermo 1 type of properties for this system. You could write down V1, U1, H1, S1. And do you think you could get, knowing that it's propane and the temperature 1 and pressure 1, do you think you could get values for V1, U1, H1, and S1 out of the tables, right? Okay, over here, you might need V1, or you might not. You might need U1, H1, and S1. After you solve a couple of these problems, you know which properties you need right away. Okay. Looking at the information, we know that the temperature 2 is 90 degrees C, but I need one more property. I need to determine one more property in order to fix the state, to jump into the tables to get the other properties. For this problem, what other property is readily determined or deduced? What's happening is this is being heated from initial, during the process, you start 1 to 2. The Q 1 to 2 is that's heat added. So many kilojoules is going to be added. And I want to know what is the state 2. How do I fix state 2? Well, it's superheated, yeah. Well, it's propane, and we have the propane table, so you can look up, if I fix the state in the superheated table somewhere, I could get the other properties. But what helps me lock in that state 2? I need 2 independent intensive properties. Is it constant pressure?
Yes.
It is. Why is it constant pressure? Because the weight doesn't change. That's right. So basically, you have to be able to see that this is 3 bar. Now that you know it's 3 bar, then you can get the other properties. True? This is a good review of Thermo 1, but now let's jump into answering part A. What is the heat transfer per unit mass? So we're asked to calculate lowercase q during the process from initial state 1 to final state 2, right? How would we calculate Q1 to 2? We got all these properties, U's and H's and S's and V's at our fingertips. Okay, so we write the first law. And the first law is written as U2 minus U1 plus any changes in kinetic, plus any changes in potential, which for this problem you can see that they're negligible. It's just gas trapped. It's not propane flying in the air or propane changing elevations. Is equal to Q1 to 2 minus work 1 to 2. True? All right. So is Q1 to 2 equal to U2 minus U1? I just get the value of U. Why did I write 1s there and they need to be 2s? Sorry about that. If that was confusing to you. Do you just get U2 minus U1? No, something's missing. Plus work 1 to 2. Is the work 1 to 2 0?
No.
I have a couple yeses, couple no's. The work 1 to 2 is not 0 because the volume changes. Can I calculate the work 1 to 2 as the integral PdV? And the pressure comes outside that integral because it's a constant pressure. And so it's V2 minus V1. True? And so Q1 to 2 is equal to U2 plus P2 V2 minus U1 minus plus P1 V1. Did I do the algebra right? And this U2 plus P2 V2 is also known as H2, and that's also known as H1. True? So Q1 to 2 is H2 minus H1. True? So we would get our value for H's, and the difference in the H's is equal to Q1 to 2. That's the answer for part A. Yes, sir?
Can you explain again why the pressure is going to be 3 bar?
Well, if I put a pin in here and held that piston in the location, and then I applied heat, what do you think the pressure is going to do to the propane? It's going to go way up. But I pull the pins out, right? Now the piston, if it becomes 3 bar plus a little bit, the piston will go up to maintain 3 bar. Put some heat, it wants to go to 3 bar plus a little increase in pressure, but the piston says, oh, you want to expand? Up I go a little bit. Yes, sir?
So safe to assume that any pistons in
Or somebody comes along and they say, there's a roof here, and I introduce a spring. What happens with the spring? I compress the spring. As the piston rises, it's now you do a force balance on that piston, and the force balance on the piston determines, oops, with the spring now, the gas pressure increases as the piston compresses the spring and goes up. But otherwise, if there's no spring, you do a force balance on that piston, free body diagram, and then see if Z, the elevation of the piston, determines the gas pressure under the piston, and the elevation does not. There's in the free body diagram, that force balance, it's irrespective of Z. Does that all make sense? So there you go. That's the answer for part A. Now, for part B, what is that change in the specific exergy? I'll put a little room down here. What we're asked to calculate is lowercase e2 minus lowercase e1, where that specific exergy. True? So is that going to be u2 minus u1 plus p naught v2 minus v1 minus t naught S2 minus S1? Is that how you calculate the change in specific exergy? We don't have to use the exergy balance equation. It's just the property. I determine it from other properties. Okay? So do go ahead and get V1s and H's and all of those properties, and you'll use them all. Okay? And if you would like the answer for this problem, I have that the E2 minus E1 is about 3.65 kilojoules per kilogram. And Q1 to 2 is 113 kilojoules per kilogram. Any comments or questions about that?